Welcome to week 2 of the JSALT Summer School. I'm Jim Mayfield. You can guess which one of these. So I'm going to be doing the morning lectures, and then Eugene is going to be running the labs in the afternoon. And these slides are a compendium of many slides from many people, including these lovely people here. Okay, so this is today's schedule. We'll have a little bit of talk about information retrieval, have a little break, have a little more talk about information retrieval, and then this afternoon in Malone, you'll have the lab with Eugene. So here's what we're going to cover. After introducing information retrieval, we'll talk about sort of 3 pieces of it: how information retrieval handles language coming in, how it does comparisons across pieces of text, and how it puts it all together in a system. So I hope we'll get through all of that this morning in the first session. And then if that works, in the afternoon, we'll talk first about how do we evaluate information retrieval systems, and then cross-language information retrieval, where you have queries in one language and documents in a different language. So what is information retrieval? It is the field concerned with the organization, storage, and retrieval of information. That information could be text, video, images, speech, anything like that. We're going to focus just on text today. And retrieving the other types of media is very important and is increasingly studied these days. But we're just going to focus on text because there's plenty there for us to take our time up. So as I said, there are 3 things we have to be able to do information retrieval. We have to be able to manipulate natural language, because we have text documents that have natural language, and we have queries that have natural language, presumably, and we need to be able to manipulate that language. And so that's done with things like tokenization and embedding. We need to compare information need that a user puts in somehow against the content of a document. That's done with things like cosine or approximate nearest neighbor search. And then we need to efficiently store and process the data using things like inverted indexes or vector stores. So these are the 3 bits we're going to talk about in order this morning. All right. To give you a sense for the kinds of tasks that are in information retrieval, there are actually many tasks that fall under this rubric, but sort of the main 3 are: first, keyword search, where you're trying to find documents that contain a single keyword, or maybe a Boolean combination of keywords. Like you type in kimchi, and you want your documents to have the word kimchi in them. Important thing about this type of search is it is a set retrieval search. That is, you're getting back a set of documents, but it's not ranked in any way. You just get this big blob of documents. The second one is what we call ad hoc querying. Given some information need that a person puts in, produce a ranked list of the documents in the order that the system thinks they're relevant. For that, we've used statistical systems until very recently. There are neural systems now that are performing better, but they're still inefficient. And one of the things about information retrieval is that efficiency has always been a big component of the study in the field, because we're dealing with very large amounts of data, and systems have to have reasonable response time. So information retrieval has always been, I think, more concerned with effectiveness, with efficiency, than other human language technologies. The third is text classification. This is sort of the inverse of ad hoc querying. In ad hoc querying, you have a fixed document collection and your queries are changing. In text classification, you have a fixed query and your documents are changing. So maybe you have, you want to know about any adverse side effect on a patient taking Tagamet. That's the kind of thing where there'll be documents coming along as they're produced, and whenever there's one that's relevant, you need to set it aside. So that's a classification problem. We'll talk mostly here about ad hoc querying, the second one. So why is it hard? Well, there are actually quite a number of reasons that information retrieval is hard. But three of the big ones are these. Polysemy, so you have words that are ambiguous, like lead or lead, however you want to pronounce that first word, depending on the context, or John Major versus Major General John Kelly. Those are different uses of the same word major. And the problem is if you're querying on some word like bank, and you want to know about money banks, and it gives you back river banks, that polysemy is giving you difficulty. Second is synonymy. So you have different words that mean the same thing. And if you put in a query about a truck, and there happen to be documents about lorries, you probably like to get those back, even though you didn't say lorry. And third is morphology. There are a lot of word forms that you have to deal with. For example, juggle, juggling, juggle, jugglers. If you put in a query with any one of those words, you'd like to get documents that talk about the other ones too. But morphology is not particularly easy. In English, it's pretty easy. So there's simple things you can do for English morphology. But in other languages, it can be very difficult to deal with the morphology. Okay, so a lot of people think that information retrieval goes all the way back to the start of Google. And for those of you who are younger than Google, that's not surprising, but there's a very long tale of history on information retrieval. And there are four related historical lines. So there's the basic text search line. There's the application of computer science to it. There's the introduction of the World Wide Web. And then recently, the use of neural networks to do the retrieval. So we're going to talk about these four lines very briefly. Text search, we can probably trace it back to the Great Library at Alexandria, 300 years before the Common Era. And that library got pretty big, especially for the time. 700,000 volumes is pretty large. And you can imagine having to retrieve particular documents in that library when you don't have electronic systems. The next thing that comes along is the idea of a concordance. And a concordance is simply an index that maps from every word in the volume to where that word is used in the volume. Okay, so the 1230s, a concordance of the Latin Vulgate, which is a very early version of the Bible. In 1247, the complete concordance of the Bible was built. And then the way text was handled was created and changed. So we had the printing press come along, and then things like the typewriter that allowed creation of much more text than could have been created before. In 1872, 21-year-old Melville Dewey invented a classification system. Anyone know the name of that system? Just curious. Huh? Yeah, Dewey Decimal System, which is the way that books used to be stored in the library. So when I was a kid, there was no Library of Congress naming scheme for books. You used the Dewey Decimal System, and it was it worked okay. Library of Congress is better, but it was the way all the physical book libraries were set up for a long time. In 1890, an exhaustive concordance of the Bible, and I think it was King James, was built. And this is an example from it. So this is part of the Strong Concordance. And you can see that it has a bunch of different words. Here's the entry for study. And if you look at the first line, it says in Ecclesiastes 12:12, there is the use of the word study. And if you actually go and look at it, we see the word study there. Okay, so this was an exhaustive concordance. Every single word was indexed, including the. It also gave pointers back to the original words in whichever language they were going back to, which probably Hebrew. So this was a way to find information in this large volume. And we're going to reflect this notion of a concordance in a bit when we talk about statistical information retrieval. Computer science comes along. I guess in 825, we found out what an algorithm was. Skipping all the way to 41, that picture on the upper right is the Mark I computer. And that's probably some small portion of what's living in your watch now. In 1945, Vannevar Bush produced a very influential paper that essentially foreshadowed the World Wide Web. So he talked about this Memex device that would help you by doing retrieval over all the things you said and all the documents you knew about in real time. And so this is essentially the sort of the first idea of the World Wide Web. In 48, many of you probably know Claude Shannon for his amazing juggling machinery. But it turns out he also made some contributions to information theory. Actually, if you've never seen his juggling machinery, you should look it up. It's amazing. And he coined the term bit and basically invented information theory, on which a lot of information retrieval is based. Let's see, computer science degrees came along, the ASCII standard was developed. So we had an encoding of letters into numbers. The first email message, I believe that's the text of it right there, came along in 72. The various companies got founded, and by 1984, we had sort of roughly modern windowing interfaces to a computer. Third, the web has had a profound effect on information retrieval. In 1984, there were only 1,000 internet hosts. The World Wide Web was invented in 1989. And by 1992, there were 1 million internet hosts, but only 50 worldwide websites. Along came some graduate students who founded Yahoo, which was a manually built directory of the web. By 1995, the Alta Vista engine was indexing 15 million pages, which was at the time was astounding. Google came along. By 1999, the Excite search engine sold for $6.7 billion. And this is last century money, right? So, and it was more than an actual car company that actually produced cars sold for it around the same time. By 2000, there were 1 billion public web pages, 3 million page index by 2002. And Bing came along, Alphabet market capitalization. I looked this up a few days ago. The market cap for Alphabet is over $2 trillion. So information retrieval is a big deal in the business world. But it's not the most recent change. The most recent fundamental change in information retrieval was the neural revolution. And this, you can trace this back maybe to 1943, when McCulloch and Pitts showed the Turing equivalence of a calculus based on neurons. That they never implemented that. That wasn't implemented until Rosenblatt invented the perceptron. And in 1969, Minsky and Papert put out a paper that said the perceptron cannot learn the XOR function. And even I said it wrong. A one-level perceptron cannot implement XOR. And everyone took that to mean that perceptrons couldn't do XOR, which is not true. A single layer perceptron can't do it, but if you stack the layers, it can. But this general perception of neural nets not being capable was one of the things that led to an AI winter around that time when funding for AI really dried up. But people kept plugging along, and backprop was popularized around 1985. In the mid-2000s, folks figured out how to use GPUs to train deep neural networks. The first real retrieval based on neural networks was, and I can never pronounce this, yeah, whatever, and Hinton, proposed semantic hashing, which was sort of like hashing, but the thing you're hashing on is not the string, but the concepts. And in 2017, attention is all you need came along, and I'm sure you've heard about that in the MT lecture, among others. And that really fundamentally changed basically everything. The Colbert system came along in 2020, which is a state-of-the-art neural retrieval system. And then the various GPTs came along and changed the way you had to think about using neural systems to do retrieval. All right. So that's the history. Any questions about the history? Okay. You are, by the way, welcome to ask a question at any time. Otherwise, you'll just hear me droning on. So part of what has been fundamental to modern information retrieval is the cost of storage. And so here we see a graph showing from 1957 that a megabyte cost $10,000. And the rapid decline in the price of space. At the same time as there's an increase in the amount of space you could put on a disk that looked like this. So these phenomena changed the way information retrieval was done, because at one point, way back when, you couldn't even store the dictionary of your words in main memory. That had to go on disk. Okay, but now you can basically store anything on disk. I was gonna ask, you probably saw it. What does a terabyte cost these days? All right, you saw it. Okay, you're too fast. Yeah, so you can get a terabyte for this. What do you think if you wanted a terabyte in 1957? What would it cost in? I guess did I do it in today's dollars? Yeah. What do you think? How many think it would cost more than $1 million? More than 10 million? More than 100 million? More than $1 billion? More than 10 billion? More than 100 billion? Okay, $10 trillion. The price of disk has come down. All right, so let's talk about the core concepts that we're going to use. Yes. Oh, yeah, I don't think you could have done it. You couldn't build it. It would be too big, I would think. In 57?
Like cassettes or something like that? Or
no, not cassettes. I don't know. That's actually a really interesting question. I don't know. Spitting platters didn't come along until the 60s, I think.
not be technically possible to store so much data.
Well, you could, yeah. I mean, if you could have a megabyte, right? So if you could have a megabyte and you could replicate that, you could, but it's just it wouldn't. Newspaper, yeah. Huh? Paper tape, maybe, although the paper tape is hard to do random access on. So, but yeah, paper tape was a way that a bunch of stuff was stored. You punch holes in paper tape according to the ASCII codes. Pretty interesting. All right. We have several definitions to do. So document, this is the retrievable unit of text. Okay, so, and information retrieval always talks about the thing you're retrieving as a document, whether it's a whether it's speech, whether it's a transcript of something, whether it's 1,000 chat messages, or it's a part of a document. Some people, especially in neural systems, now you have to chop documents up into segments. The thing you're retrieving, we're going to call a document. A whole bunch of documents is called your collection or your corpus. The plural of corpus is corpora. And so this is a set of documents to be searched, and we talk about the collection size as the number of documents in that collection. An indexing term, or also called just a term or a token, is some word, phrase, or lemma, or stem, or subword that you're using as the unit of expression for the meaning of the documents and the queries. Your dictionary is also called the lexicon, also called your vocabulary, is the set of word types, or yeah, we're going to call it, well, term types that you have. So if you're doing an English index, your dictionary is going to be a big set of English words. And the number of words in your retrieval system can be in the millions. So it's not, you're not going to have billions of terms, but you're going to have quite a few. A topic is a description of what the user wants to find. Okay, so it's an expression of their information need, and not necessarily in any form. We just talk about the topic as some sort of description of what they're looking for. And this is not the same as a query. A query is something you actually send to your retrieval engine, and there's a gap between information needs that users can express and what you have to put into the system. So we make that distinction. Some other core concepts. Oh, by the way, so this picture is core memory. This is how main memory was done back in the 60s. You had these ferromagnetic cores, and you had wires running through them, and you'd send a pulse through this way and pulse through this way and measure what happened, and that was 1 bit. And these were actually little rings that you could see. They were big enough for you to see them, and each one was a bit. So you can imagine you couldn't put too much of that together. Okay, a relevance judgment is an opinion about the degree to which a document is relevant to an information need. Okay, now this is a really weird concept for natural language processing folks, that it's an opinion, not a fact. And this is one of the things that has separated information retrieval from other natural language technologies. We'll talk more about that in a bit. Relevance judgments can either be binary. Yes, this document is relevant, or no, it's not. And a lot of the history of information retrieval has been done with binary judgments. But it can also be graded. So for example, you might say, this document is highly relevant. This one is somewhat relevant. This one is not relevant. We'll see a little more about that as well later on. Then there are a number of counts that we deal with. The document frequency is the number of documents in the collection that contain a particular term. So for example, the term "the" in an English document collection of 1 million documents, the document frequency for "the" is around 1 million, because almost every document is going to have the word "the" in it. On the other hand, the word kayak might be in only 10,000 documents. It might occur 18 times in every one of those documents, but the number, it's just the number of documents that's the document frequency. Collection frequency is the number of times the term occurs in the corpus. So this does take into account the number of times the term appears in any given document. And of course, the collection frequency of "the" in a 1 million document collection is going to be well more than 1 million, because most documents are going to have many uses of the word "the." Term frequency is the number of times the term occurs in a specific document. Okay, so we might have document 5 that has 3 occurrences of the word "people." So its term frequency is 3. Now these are all absolute counts, right? This is counts of the number of occurrences of a word in some set. These can all be made relative. where you simply normalize by the total number of documents or the total number of tokens or the total number of tokens in the collection or tokens in the document. And so these are referred to as relative document frequency, relative collection frequency, or relative term frequency. People in the literature will abbreviate relative collection frequency to collection frequency. Okay, so when you see these terms, you have to pay attention. Is this normalized or not, right? Is this 0 to 1, or is this an absolute count? But this is how we're going to use it. Relative means normalized. And if you don't, it doesn't say relevant, it's not normalized. Questions about these, any of these definitions? Okay, so the first of our 3 pieces of information retrieval is how do you deal with the language that's in the documents or that's in the query. Tokenization is how we refer to chopping a document or a query up into the tokens, the bits that we're going to use for indexing. So here's a document that exhibits a number of issues for tokenization. There's 2020, and you might wonder, well, how am I going to index that? That might be indexed as the year 2020, right? You might have separate tokens for years, or it might just be indexed as the number 2020. Or for some systems, you might just want to know it's a number, right? So that's an issue. Madlib-esque. Anyone not know what a madlibs is? Okay. Okay. Now, Madlibs is a game where there's a text, but a bunch of words have been eliminated from it, like maybe nouns and adjectives have been eliminated. And people around the party say, okay, give me an adjective, give me a noun, and you fill them in the blanks, and then you read the story, and it's very funny, haha. Yeah. So, Madlibs-esque. How many tokens is that? How many people think 1? 2? Okay, a few 2s. 3? A few 3s. 4? Okay. The answer is, it just depends on how you do it, right? It depends on what your purpose is and so on. It actually could be more if you're chopping it up into pieces. These are issues in tokenization, and there are lots of these issues that you have to figure out how you're going to deal with when you're tokenizing. One of the advantages of the recent neural approaches is that you have very few of these decisions to make, and we'll see about that in a bit. So if you are doing explicit tokenization, there are a number of tokenization steps that happen, and you need to know about these just in case you're reading the literature and you see these concepts. Obviously, case folding, mapping everything to, say, lowercase, is often done in many systems. It's not done as much in modern systems because there's enough data that has capitalization to be able to make distinctions. Back in the day, when there wasn't so much data, you didn't have, you couldn't distinguish, you didn't have enough training data on, say, the capitalized version of a word to get good statistics on it. Stop word removal is throwing away words that aren't going to help you. So most systems that use tokenized with English words will put the in the stop word list. Means anytime they see the word the, you just throw it away. Now, this doesn't really have much of an effect on the effectiveness of the system, but it does have a strong effect on the efficiency of the system, because you can imagine if you want to have you're building a concordance essentially, and you say the, you want to have a pointer to every document that contains the. That's a lot of space that's pretty much wasted. So stop word removal is often done, but it's mostly for efficiency. And then there's word form normalization. Stemming is a common one. Stemming is simply suffix removal. You build a system that chops off the ends of words. So you might have golfing, golfers, golfed. all of them, you chop off the end and transfer them all to golf. And that way, if you have some query about golf and there's a document about a golfer, you find it. An interesting fact about counting words is that words in natural languages typically follow Zipf's law. And Zipf's law says, one way of saying it is the kth most frequent term has frequency proportional to 1 over k. Or another way to say it is that the product of the frequency and the rank is constant. So here's an example of one English collection that has been where we've counted all the words, and counting words is a big thing in information retrieval. We've counted all the words, and we see that if we put it on a log-log scale with frequency on the y-axis and rank on the x-axis, we get this pretty much a straight line. At the upper left is the very frequent words. At the lower right are the words that only occur once. And these are called hapex legomena. I've never known how to pronounce that. I've been teaching this for many years. No one's ever been able to tell me. It's probably, I could probably look it up. But anyway, that just means a word that occurs only once in your collection. Okay? And about half of the terms in your collection only appear once. So when we're talking about word frequency, from a retrieval perspective, not all frequencies are equal. So here we have again a plot of words in rank order against frequency of the words. This is not a log-log scale, so that's why it's not a straight line. But we see here over the left the most frequent words, like the, a, and, they're not very discriminative. That is, you want an indexing term to discriminate documents, discriminate the documents that are relevant from those that aren't, right? So if the is in every document, putting the in your query doesn't help at all because it's not going to distinguish some documents from others, right? So the very high frequency terms aren't discriminative. And so we don't really like them as indexing terms. At the same time, the rarest words can really only affect very few documents. So while they may be important for those few documents, in general, they don't affect the ranking of many documents. So we like to have the significant words from a retrieval perspective as the main terms we look at. And these occur in the middle of this range here. Questions on counting words? Okay, so we can count these things, but how do we find them? Well, first we have to segment the text. And there are at least three levels of segmentation you need to do. You need to figure out where the sentences are. Then you need to figure out where the words are. And then you might have to figure out where the parts of the words are. So we'll look briefly at these. Sentence boundary detection in English is actually pretty hard. In some languages it's not because there's like the Chinese full stop character is an unambiguous end of sentence marker. Periods in English are a big problem. Dr. Mulholland of Mulholland Drive says that in other languages, sentence segmentation is not so easy, et cetera. There are 6 periods here, only 2 sentences. Okay, so how do you know whether a period ends a sentence or not? That's a problem. And for something like machine translation really likes to have parallel sentences. Right? So if you're building this big parallel collection, you want the things on both sides to be sentences. So you want to be able to find where they are. And you can do that rule-based or through machine learning. Word boundary detection in some languages is pretty easy. So English makes it fairly easy because we have a space between words typically. In other languages like Chinese, all the characters get run together. So you don't know where the words are. In fact, a lot of use is made out of that because you can embed ambiguities in your text that convey more information than just a single one best interpretation. Doing word boundary detection can be done rule-based or through machine learning, or you can just ignore the problem. And this is where we're going to end up. Morphological segmentation is breaking apart a single word into its morphological components. I'm not going to talk too much about that here. Let's say here's a Finnish example. And Finnish has a huge amount of morphology. And so you can have 100 different word forms for a single root. This is an example of an attempt to automatically segment this word, which means congressman, into its component parts. And there are a lot of different morphological processes that you need to deal with if you're doing morphology. Things like compounding, where in some languages like German, you can take two words that are good words, you can glue them together to form a new single word, perfectly legitimate German word. It's never been seen before, it will never be seen again, but it's a legitimate word. You just shove these two smaller words together. Okay. So to effectively retrieve based on German words, you have to have some sort of segmenter that will decompound the word. And so there are all these other kinds of morphology that you may have to deal with. And old-time systems spent a lot of time figuring out how to handle such morphology. One of the main ways, as I said, was stemming. It's applicable to alphabetic languages. It's an approximation to lemmatization. So lemmatization is finding the actual root of the word. Stemming just fakes that out by just chopping off the end. Most stemmers are rule-based. So here's an example of a very simple stemmer that maps juggling, juggles, and juggle to the same term. Now, there's a famous English stemmer called the Porter stemmer. It was a rule-based stemmer, and it became very popular. And it got so popular that everybody who wrote a rule-based system called their system a Porter stemmer, even though it was not the Porter rules. So Porter got frustrated and set up this snowball project where this is sort of Porter by Porter, and it has an English stemmer and stemmers for other European languages. So if you happen to need a stemmer for a European language, this is a reasonable place to go to get it. Okay, subword representations. This is how things are done now, typically. So with subwords, you're using pieces of words for indexing. So you're chopping the words up somehow. So let's say this is our text. Awesome sauce, chillax, and Fitspiration are recent portmanteaus. How are you going to index this? You can imagine that if this were a document, these terms are probably not going to be very frequent. They're fairly recent coinages. So we're going to break these terms up into pieces. And there are two main ways to do that. The old way is called character engrams. And in character engrams, you pick some n, like 5, and you chop your text up into overlapping sequences of 5 characters. Okay. So this is the start of the character 5-gram tokenization for this text. Blank AWES, AWESO, WESOM, and so on. Okay. So each character is appearing in more than one token, which has implications. But this is how subword tokenization was done for a long time. And it was really effective. There's really interesting history, which I don't have time to get into now, but if anybody wants to hear an amusing story about an article in Science that was controversial, you can talk to me later. So that's the old way. Byte pair encoding is the basis for the new way of doing things. And the idea behind byte pair encoding is that you're not doing overlapping pieces. You're breaking the words up into sensible pieces. For some definition of sensible. So here you can see that there's a byte pair encoding breakup of this text. And you can see the subwords are variable length. Right? And this is the way tokenization has been done, say, for the past 6 or 7 years, maybe. Subwords has some real advantages over other kinds of tokens. So they counteract data sparsity. So if you have, you're training on some collection, and you have very few occurrences of some term, or there's some word that's out of vocabulary, okay? It's just not in your collection. What do? If you're just using words, that term is lost as an indexing term, right? But if you can break it down into pieces in such a way that the pieces occur in the document, even though that particular way of putting them together does not, then you have a much more effective system because you're getting information about parts of the word, even though you don't have information about the whole word. Right? There are some disadvantages. The two main disadvantages are that they tend to build larger indexes because not every character begins a word, but every character begins a character engram. This is not so much true of the byte pair encoding, but the other thing is that they tend not to play well with word-based systems. So if you do everything in terms of pieces of words, and then you have some system over here that deals with words, a parser or something, you have to have some way to glue the pieces back together. And so that's an issue for these types of tokens. Here's just a comparison. This is just character engrams. And you see here a chart of, I believe this is a measure called mean average precision. Virtually every measure in information retrieval has the bigger the number, the better. Okay, this differs from like word error rate or something where you're trying to drive it down. If you're in information retrieval, you can almost always rely on the fact that the bigger the number is, the better the system is. Okay, so these graphs are showing this mean average precision performance over several different languages according to different tokenizations. So the very first one is just using words, break the words apart, you don't do anything to them. And you can see that performance is generally lower for all these languages. If you use some sort of stemming, performance gets a little better. But if you do character engram tokenization, you can see that for some languages, it doesn't really matter. English and Spanish, maybe do a little better, but not a lot. But for morphologically complex languages like Finnish, you get a huge benefit out of it because the pieces of words are capturing that morphology where you don't have any information about the word as a whole. So subwords are a really powerful way of tokenizing. So as I said, byte pair encoding is the technique that is used now, or the technique underlying what's used now. They put bells and whistles on it, but so this is how we do byte pair encoding. You start with some big training collection, okay, just some big wad of text. And then you take each character that's in that text and treat it as a single token. Okay, so you start with an inventory of a bunch of letters. Okay, here in our example here, our training collection is she sells seashells. And so we start with these 6 tokens. And what we're going to do is repeatedly find another token and add it to our inventory. Okay. So we do that by finding the most common adjacent pair of tokens. So here in our example, blank S is the most common character bigram in this text. So we take blank S and we add it as a single token to our inventory. And then we replace all the blank S's with this new token. Okay, so we have increased the size of our subword inventory, and we've shortened the training text a little bit. And we just repeat that. Okay, so LL is the next most common one. We add LL as a token and replace all occurrences in the training text with LL. Yes. Oh, the question is, why does it choose LL, not EL? They occur the same number of times, so it's just random. Yeah.
I mean, 3 letter words and 1 letter, 2 letters.
So the question is whether when you have a choice, is there a preference over putting together longer ones or more words or so on? And that is a decision that particular systems make decisions on. And it is an issue because you can end up here with multiple ways to tokenize a string, and so different subword segmenters will handle that issue differently. Okay, yeah. So the most common pair might include previously made tokens. So here, LL followed by S is the most common. So we make a new token LLS and replace all the LLSs with that token. Like so. Okay, so this is how it works. You keep doing this until you get a desired vocabulary size. Okay, so in this approach, you get to choose how many token types you have. And that's how you decide how to stop. So here are some examples. Yes.
So generally, the algorithms are greedy.
Yes.
Is there some global optimal algorithm that would like choose all the possible combinations and pick the best one?
Well, so I don't think there's any one. Let me just point here and then I'll talk about that. So there are sort of two main flavors that are used these days often, word piece and sentence piece. And they handle these questions differently. Okay, so for example, in word piece, you have to segment the words first. Okay, so you have to have a word segmentation. You do that step before you do the tokenization. That means that it works fine on English, maybe not so well on Chinese, because you don't know where the word boundaries are. In contrast, sentence piece doesn't require you to find the word boundaries. Okay, so decisions like that are going to control what it means to be the best breakdown. Okay, and the sentence piece actually does a bunch of other stuff to try to have a unique tokenization and to make sure you're getting efficient breakup of the word. So there's an alternative version that starts with all the possible terms and then whittles them down. Okay, that is used too, and there's a part of sentence piece I think that does that. But the details get complex, as you can imagine, because there's a lot of phenomena you have to deal with.
Because I'm from Vision and I read papers that use PPE. So first of all, is there like consensus on this? Like, let's say there's one tokenization that's already been done on a few people or something like that, or everybody?
Yes, there is. The question is there a consensus on how to do this? The answer is yes. Word piece and sentence piece. Okay. So, and it's important because to jump ahead, BERT is a particular language model that uses this word piece tokenization. Okay. If you are going to use BERT, you must use that tokenization. Okay. You can't say, oh, I like this tokenization better, I'm going to use that, because then it's not going to align with the language model. Okay, so you have to use the tokenization of the original language model. So really, that means you have no flexibility, because the language models that are out there, you're not going to create a new one, right?
Okay, so in Vision we have this same. We have foundation or backbone models that are pre-trained on some large corpus. So, and everyone is using the same weights. So I can imagine the same is going on with the PP. Like everyone is using the same,
Yeah.
Sorry?
In machine translation, you have some training data, so you train the vocabulary of the data using the algorithm.
You do?
Yeah, very fast.
But then you created your own tokenization that you can use only with your model, and you have to distribute it with the model. By image,
Yeah.
like,
Right, but for machine translation, for those online, the questions are about parallels between essentially the equivalent of tokenization in vision and in machine translation. And in machine translation, you can make up your own tokenization because you're really only caring about the parallel sentences. You're typically not going through, not piping through an existing language model, right? Whereas I think in vision, it sounds like you cannot. You have to use what everyone else has used. Is that right?
well, you can, but they make it hard for you. So I mentioned it's the same bird. Yeah, I don't know. I will use just the tokenization that was pre-trained on some data set.
Yes.
I will just use it, not create
That's,
my
yeah,
own.
yeah, you just have to use the BERT tokenization. Because it's the only thing, it's the only entry into BERT is through these tokens. Right.
Otherwise, I would need to train the bird from scratch on my data. Let's say.
Yes, I mean, you could do that if you want. You can train your own. Back a few years ago, people did that, but okay, somebody remind me when our break is, and we'll get it. What was it? Break is when? 10:20. Okay, great. Questions?
Maybe have the frequent, I also have the frequencies of the individual tokens, right? So do I do it greedily, just
Yeah, okay. So yeah, the question is, you've got these tokens. How do you now tokenize a new thing? And you use the software that that they used, but it's a lot like you typically don't do this yourself, right? If you were building your own model, then you would have to decide how to do that, right?